Welcome back. We're going to focus on our first section out of Chapter 2 today. We're going to look at trig functions of acute angles. I mentioned in 1.4 that we're going to focus on defining our trig functions in different ways this semester. In Chapter 1, we used angles in standard position. As we defined our trig functions. We set that angle in standard position. We talked about x, y, and r as our three values. So for example, our sine function for theta is y over r when we are using our angle in standard position. Now, we're going to be using ratios of sides of a right triangle. So instead of creating a right triangle from an angle in standard position, we can be talking about any right triangle anywhere out in space. So instead of sine theta being y over r, now we're going to talk about sine of theta as the opposite side over the hypotenuse. And this may sound really familiar to you from high school trig. You probably memorized it as SOHCAHTOA. I did not memorize it that way, so I don't feel comfortable talking about it as SOHCAHTOA. I just remembered opposite over hypotenuse, adjacent over hypotenuse, and opposite over adjacent. Anyway, so this gives us our starting place with something we're familiar with. We've got an angle theta in standard position. So here's our angle theta that we're interested in. We have our initial side and our terminal side as the value for r. And we've created from this angle theta, though, when we drop that perpendicular line, we created a right triangle. Now, the side opposite the right angle is always the hypotenuse. That's the longest side in my right triangle. Which one we're discussing as opposite or adjacent is determined by which of my other two angles, not the right angle, it is that I'm referring to. So if this is my angle theta, this side is the side that is adjacent to theta. It is one of the rays, one of the sides that builds that angle that I'm looking at. And if this is the side that is adjacent to the angle, this is the side that is opposite the angle that I'm interested in. So in this particular figure, the side length y is my opposite side, or the side opposite my angle. Oh, and it labeled angle as angle A. I'm sorry, not theta. And the length of side x is the side that is adjacent, so the side adjacent to that angle A. So I see that sine theta, instead of being y over r, would be opposite over hypotenuse. Cosine theta, instead of x over r, would be adjacent over hypotenuse. And finally, tangent theta, instead of y over x, is going to be opposite over adjacent. And there's that SOHCAHTOA. SOHCAHTOA. If you don't know what I'm talking about, don't worry about it. All right, and then we have our reciprocal function values. Cosecant is hypotenuse over opposite. Secant is hypotenuse over adjacent. And cotangent is adjacent over hypotenuse. Okay. So let's talk about why this always works, and the important part is figuring out which angle you're talking about. So we've got angle A and angle B here. C is my right angle, and you're going to see that that's pretty standard for this book in particular, but typical that C is going to be the right angle, so that side C, the angle opposite C, is going to be my hypotenuse. So we are interested in function values for angle A and then in function values for angle B, but notice we're just doing our three basic function values. So let's start with angle A, and we're going to look at sine of A, cosine of A, and tangent of A. So if A is the angle I'm interested in, sine is opposite over hypotenuse. Well, the side opposite A is 36, hypotenuse is 85. So I've got 36 over 85. Cosine of A is the side adjacent over hypotenuse, so 77 over 85. And then tangent of A is opposite over adjacent, so 36 over 77. Now we also want to do the same for angle B. Angle B is over here. So now if I'm looking at angle B, the hypotenuse is still the same. The hypotenuse is going to be this 85. It's opposite that right angle. But the side opposite B is the other side. I've just switched the orientation. Now since my focus is over here on angle B, 77 is the length of side opposite, and 36 is the length of the side adjacent. So let's set up our three main trig function values for angle B, focusing again on this as my angle B. Sine is opposite over hypotenuse. Cosine is adjacent over hypotenuse. And tangent is opposite over adjacent, in reference this time to angle B. Now, do you remember us mentioning our cofunction identity? When I look through these lists, I see that we have some things in common. I see that my cosine of B is the same value as the sine of A. And I see that my cosine of A has the same value as the sine function for angle B. Now, sine and cosine are cofunctions. What is special about angle A and angle B? Well, the sum of the angles in my triangle is 180 degrees. So if C is 90, that means that these two have a sum of 90 as well, and they are complements of each other. My cofunction identity, if you remember, my cofunction identity said that cofunctions of complementary angles are equal. Cofunctions of complementary angles are equal. Sine and cosine are cofunctions. Now, tangent and cotangent are reciprocals of each other. This tangent function value is going to be equal to the cotangent function for B, because they are cofunctions of complementary angles. Cofunction identity. The cofunctions of complementary angles are identical. They're equal. So anytime I have a right triangle, the other two angles, not the right angle, are complementary because they have to add to 90 degrees, and we get to apply our cofunction identity. Now back to your identity sheet. That cofunction identities, we're going to focus on them a great deal in Chapter 5. Here's my cofunction identities set up, showing which functions are cofunctions. If theta is one angle, 90 minus theta is its complement. Okay, let's look at the next page and do a little bit of application of this. Well, first we're going to get it kind of down and defined, and then we'll do a little bit of application. Okay, because we have a right triangle, we know that angle A and angle B are complementary angles. Their sums are 90 degrees. Then I know that, for example, A over C, well, if I'm referencing angle A, side A is opposite. So that would be opposite over hypotenuse. So that's sine of A. That's going to be equal to the cosine of B. If I'm looking at angle B, A is the adjacent side. Well, let's look back here at angle A again. A over B. A over B. Opposite over adjacent is tangent. So tangent of A is going to be equal to the cotangent of B. Where I have angle B, A over B is adjacent over opposite. If I'm focusing on angle A and I have C over B, C is hypotenuse over adjacent. Hypotenuse over adjacent is adjacent over hypotenuse would be cosine, so that's going to be secant, which means this one is going to be cosecant of B. So those are my cofunctions. Cofunctions of complementary angles are equal. And there is my definition for my cofunction identity, as well as that list that shows up on your identity sheet. Okay, so let's make use of this cofunction identity. We have to identify both pieces. What is going to have the same measure as the sine of 9 degrees? Well, the cofunction of its complement is going to be equal. So when I take the sine of 9 degrees, that is going to be the same thing as the cosine of 81 degrees. Let's check this with our calculator because we have sine and cosine buttons, so we can absolutely do this one. Now, when I'm doing trig functions, I want to make sure I'm in the right mode. You have a degree button. If I push this degree mode, I have, these are the two that we're interested in, degrees and radians. We're not going to do gradients. Degrees and radians. Now I'm in degree mode, that's where I need to be, so I'm going to hit enter. Sine of 9 degrees, and it's going to give me an approximation. And I don't need to worry about a degree symbol because I'm in degree mode. Sine of 9 degrees is 0.1564, and then it rounds it off when I run out of screen. So keep that in mind, 0.1564. If I plug in cosine of 81 degrees, also 0.1564. These two values are equal to each other. Okay, let's do the rest. What is my cofunction here? Well, cotangent, the cofunction is tangent, and I don't just copy down that 76. I have to use the complement of 76. The cofunction of cosecant is secant, and the complement of 45 is 45 because 45 plus 45 is 90 degrees. Now notice I remembered my degree symbol on all of these, so I'm saying degrees, not radians. All right, let's solve some equations using our cofunction identities. Find one solution for each equation. We're going to assume that all angles are acute angles because remember we have options that are not acute angles, but we're going to keep it simple for now. Now, cotangent and tangent are cofunctions. That means that if these two values are equal to each other, these two angles have to be complementary. So together, these two angles are going to equal 90 degrees. So I've got theta minus 8 plus 4 theta plus 13. Well, 90 degrees is going to be equal to 5 theta plus 5 because negative 8 and 13 gives me a positive 5. When I move that 5 over, I'm going to have to subtract it. So 85 degrees is equal to 5 theta, and theta comes out to be 17 degrees when I divide out that coefficient 5. Alright, you take a go at the next one, pause the video for a second, see what you can do with the next one using your cofunction identities. move on to our next example. Okay, we're going to be comparing function values of acute angles. As we rotate through, what is happening to our sine, cosine, and tangent function values? We're going to keep it restricted to those three main trig functions, and we're going to be focusing right now particularly on quadrant 1, because as we move around the full circle, things change, but we are going to be focusing in particular on quadrant 1. I've got 3 unit circles drawn here. I know it's a unit circle because if you can read the coordinates, my coordinates are at 1 and -1. All right, we're going to have an angle A, and we're going to show that angle A is increasing. So as angle A increases, what's going to happen? Okay, so I'm going to show a very small angle A, and then it's going to get a little bigger, it's going to be growing, and then it gets bigger as I move through quadrant 1. So you can see my angle A is rotating in a counterclockwise manner so that the angle is increasing. Well, what happens as I drop this perpendicular and I'm looking at, in particular, the 3 parts of that angle, the radius, the sine, and the cosine function value, what is happening? Well, the radius, this r value, it's on the circle, right? It's the radius of the circle. The circle isn't changing side, so that radius, which is my hypotenuse, stays the same. The radius stays the same. Now let's talk about what's happening to y, the sine function value, or the side, if this is my angle, it's the side opposite. So that opposite side, which is also the sine function value, what's it doing? Well, that sine function value is that y segment, and I can see that as my angle is increasing, this y segment is also growing. It's getting longer. It's also increasing as that angle A increases. And then finally, I have, if this is my angle A, my adjacent side is that x coordinate. So that adjacent side, which is my cosine function value, the x coordinate, what is it doing? Well, when I look at it, my x coordinate to the perpendicular is long, and it gets shorter, and it gets shorter. So it is decreasing. As angle A increases, that adjacent side is decreasing. So the hypotenuse is staying the same. So the sine and cosine function values are increasing or decreasing against or relative to that hypotenuse that is staying stable. So what can we talk about as far as sine, cosine, and tangent of angle A? So as angle A increases through quadrant 1, we're going to be looking at sine A, cosine A, and tangent A. Now sine A is opposite over hypotenuse, cosine A is adjacent over hypotenuse, and tangent is opposite over adjacent. Well, if the hypotenuse is staying the same and the opposite side is increasing, then that means the sine function value is increasing through quadrant 1. As my angle gets larger, my sine function value is increasing. What's happening to cosine? Well, since the hypotenuse is staying the same, I can see that my cosine function value is decreasing. It's getting smaller through quadrant 1. And then if I look at tangent, tangent is opposite compared to adjacent. Well, if that opposite side is increasing and the adjacent side is decreasing, then my tangent function value is also increasing through quadrant 1. Okay, now how are we going to use that? we're going to use this information to determine, to figure out whether each statement is true or false. Now, to do that, you have to be able to think about your cofunction identity as well as that inequality statement. So this is a less than, C is greater than, and D is less than or equal to. Okay, so tangent of a 25-degree angle would be less than a tangent of a 23-degree angle. Now 25 and 23 both in quadrant 1, and we said that as we move through quadrant 1, our tangent function value is increasing. So as A gets bigger, tangent gets bigger. So is this true or false? Well, this is going to be false, because this says that as the angle gets larger, the tangent function value is less than a smaller angle. And we just said tangent is increasing. So that's not true. Okay, let's look at, these are both reciprocal function values. So let's actually skip down here and look at C first. Sine of a 21-degree angle is going to be greater than sine of an 18-degree angle. True or false? Well, we said as A increases through quadrant 1, our sine function value is increasing. So is this true or false? Sine of 21 degrees is greater than sine of 18 degrees. Yep, that's true. That one works. Okay, so now let's compare B and D. So with B, I can't think in terms of cosecant. So I need to put this in terms of its reciprocal function. So if I do sine is the reciprocal of cosecant, right? So I want to look at the sine of a 44-degree angle, and I want to see how it compares to the sine of a 40-degree angle. Well, sine is increasing, so sine of a 44-degree angle is going to be bigger than a sine of a 40-degree angle. So what happens when I switch those numbers? So if I take the reciprocal, now let's just do a let's suppose, okay? I don't know what the sine of 44 is, and I don't know what the sine of 40 degrees is, but when I flip this, what happens? Let's pick an instance, for example, over here to the side, where we have a fraction that is larger than another fraction. Well, 1/2 is greater than 1/3, right? 1/2 is greater than 1/3. 1 out of 2 is a bigger piece of pizza than 1 out of 3. If that bothers you, if you want the same denominator, let's say that 2/3 is greater than 1/3. 2/3 is greater than 1/3. That one's really clear. Well, if I flip those upside down, because that's what I'm going to do here, going from sine to cosecant. If I flip those upside down and I say, okay, what about cosecant now? How is the cosecant of a 44-degree angle going to compare to the cosecant of a 40-degree angle? Well, let's take the reciprocal. Reciprocal of 2/3 is 3/2, and the reciprocal of 1/3 is 3/1. Now, which one of these is bigger? Well, 3 is more than 3/2. That's just 1.5. So 3/2 is less than 3, which means if this is a greater than situation, when I flip it, it reverses and becomes less than. That's what this says. So that is true. Now, we're going to reason through one more like this. This is my way of reasoning. If you don't like it, you're going to have to find your own way, or go to my math lab and see if their way of walking you through makes more sense to you. This is just how it makes sense to me. So we're gonna do this one more time with D, and hopefully it will click if it didn't click on that last example. All right, secant. The reciprocal of secant is cosine. So we've got cosine of 56 degrees compared to cosine of 49 degrees. And I go back up and I say, okay, as my angle increases, my cosine function, my x-coordinate is decreasing as the angle increases. So that means that the cosine of a 56-degree angle is less than the cosine of a 49-degree angle. But I'm not interested in cosine, I'm interested in secant. So I'm going to take the reciprocal of those and see what happens with the reciprocal of those. So I'm going to set up a situation just with random fractions for examples, and I'm going to say, okay, I need a fraction that is less than another fraction. 1/3 is less than 2/3. When I flip those upside down, take the reciprocal of those, 3 is greater than 3/2. That relationship reverses so that I know that the secant of 56 degrees is actually greater than the secant of 49, which is not what that says. So this statement is false. All right, hopefully that made sense. Let's go ahead and move on. We've got a couple of more pages in this section to get through before we stop. Trig function values of special angles. Now we've got some special triangles formed here. This first special triangle is equilateral, and I know it's equilateral because each of my sides is marked to be the same length and each of my angles is marked to be the same measure. So let's just throw some measures on here and say that this equilateral triangle has side lengths of 2. Well, if I drop a perpendicular here, I know that this would be a right triangle. That is going to bisect that angle, right? So if it's equilateral and these three angles are equal, that means they all have to be 60, 60, 60, 60, because 60, 60, 60 adds to 180 degrees. That means this is a 60-degree angle, and when I bisect it and cut it in half, this is a 30-degree angle. So I have a 30, 60, 90 right triangle here. Now this is side length 2. If I cut it in half, this is side length 1. I don't know what this is. So let's figure it out. 2 is the length of my hypotenuse. So if I've got a squared plus b squared equals c squared, this 2 goes here. So that's 2 squared. Let's just make that a as 1. So 1 squared, that means this is side b, b squared. 1 squared is 1. 2 squared is 4. So b squared is going to be equal to 4 minus 1 is 3. Which means b, when I take the square root of both sides, is square root 3. b is square root 3. So if I have this right triangle, my measurements are 1, 2, and square root 3. What's that going to give me if I'm looking at, let's say, the cosine of a 30-degree angle? Well, cosine is adjacent over hypotenuse. Here's my 30-degree angle. That would be square root 3 over 2. Sine of a 30-degree angle. Well, that would be opposite over hypotenuse. That would be 1/2. And tangent of a 30-degree angle would be opposite over adjacent, which would be 1 over square root 3, or square root 3 over 3. Now let's look at this one. Nope, let's go down. Oh dear, I should have picked different values because this set it up. You know what, we're going to change these values. Change these values with me. Because we have 1, 2, and square root 3, 30, 60, 90. Let's change this. Let's make this, one 3. Oh, I can't do that. That's 2 and 1. Let's make this one 6 and this one 3. And see what that's going to give me. If this is 6 and this is 3, yeah, that's good, because that whole thing would be 6 there. I'm sorry. I'm talking through stuff as we go. So a squared plus b squared equals c squared. That would be 9 plus b squared equals 36. So b squared would be equal to 27. So b is going to be the square root of 27. Square root of 27, 27 is 9 times 3. So that's 3 square roots of 3. So this side then is going to be 3 square roots of 3. So let's check out cosine, sine, and tangent now and see what happens. So cosine of 30 degrees, sine of 30 degrees, tangent of 30 degrees. So these are both 30, 60, 90 right triangles. 30, 60, 90, 30, 60, 90. But this measures were 2, 1, and square root 3. Now we've got 6, 3, and 3 square roots of 3. Let's see what happens. So cosine of 30, cosine is adjacent over hypotenuse. So that comes out to be 3 square roots of 3 over 6, and I need to simplify. Well, both of these have a factor of 3, so that simplifies to square root 3 over 2. Sine of 30 is opposite over hypotenuse, so 3 over 6 is 1/2. Tangent of 30 is opposite over adjacent, so 3 over 3 square roots of 3. When I rationalize and simplify, comes out to be square root 3 over 3. It did not matter what my original lengths were. The cosine, sine, and tangent function values for my 30-degree angle are the same, no matter what, because those ratios simplified to the same values. So it doesn't matter how big or small my triangle gets, what those measurements get to be, those trig function values are going to have the exact same ratio. So we just found sine, cosine, and tangent for a 30-degree angle. We found that sine is 1/2, cosine is square root 3 over 2, and tangent is square root 3 over 3. Now, let's come up here and look at this triangle. This is a different type of special triangle. This one is isosceles. My sides are marked here so that this one's 8. That means this one is also 8. This is 90 degrees. If these sides are the same length, these angles are the same. They have to be complementary, so they're both going to be 45-degree angles. That's the other special angle on my unit circle. Okay, so let's figure out the length of that hypotenuse if this side length is 8. Okay, so we've got 8 squared plus 8 squared equals c squared, where this is my c. 8 squared is 64, so 128 equals c squared. So c is going to be square root of, well, 128 was 64 times 2, right? And 64 is, the square root of 64 is 8. So c is going to be 8 square roots of 2. 8 square root 2. That's my value for c. So there are my values for this isosceles triangle. Let's do cosine of 45, sine of 45, and tangent of 45. Both of these angles are 45-degree angles, so it doesn't really matter. Cosine is adjacent over hypotenuse, so 8 over 8 square root 2. Well, that 8 is going to cancel out, and when I rationalize my square root 2, that's just 1, I get square root 2 over 2. Sine of 45 degrees, opposite over hypotenuse, is going to start out the same way, so it's also going to reduce down to be square root 2 over 2. Tangent is opposite over adjacent, so in this case that's 8 over 8. It's always going to be 1. No matter what that initial side length started out to be, the ratios are always going to simplify to be these values. I can come down here to my 45-degree angle, and I can say sine is square root 2 over 2, cosine is square root 2 over 2, and tangent is going to be 1 every single time, no matter what size I start with. Because I know my 30-degree angle, I can fill in my 60 because sine and cosine of complementary angles, those are my cofunctions. So sine and cosine are going to be the same value. Instead of square root 3 over 3 for tangent, I'm going to take the reciprocal of that. It's going to be square root 3. And then I can find my reciprocal function values from those original 3 values. I want you to we're going to work through them for the 30-degree angle, and then I'm going to fill them in, and I want you to come back later and make sure you understand, or you can pause the video and fill them in. Okay, so if I take the reciprocal of tangent to get to cotangent, I have 3 over square root 3, which just simplifies to be square root 3. The reciprocal here, I'm going to flip it and then rationalize it. becomes 2 square roots of 3 over 3. And the reciprocal of sine is cosecant. That's just 2. The reciprocal of 1 is 1. The reciprocal of square root 2 over 2 is square root 2. Same thing here. The reciprocal of square root 3 is square root 3 over 3. The reciprocal of 1/2 is 2. And the reciprocal here, square root 3 over 2, becomes 2 over square root 3. When I rationalize that, I get 2 square root 3 over 3. So there are your trig function values for your special angles. We've already done those on your unit circle. So hopefully you remember doing those from the unit circle. All right, let's go through the last couple of examples. Finding these function values, or the values, these function values for the lengths, finding the lengths for each of these triangles. Alright, so whenever you're solving like this, one thing that you need to remember is that you want to use your givens as much as possible. Use the things you are given as much as possible, because you know that those things you are given are right. If you use found values, things that you figure out, you're going to have to take a chance that you might have made a mistake. But if you use the given values, then you can be confident that you're right. Okay, so I've got some angles I can fill in here. Let's start with that. This is a right triangle, so this is going to be a 30, 60, 90, and this is going to be a 30, 60, 90. The only side length I'm given is this 9. Let's start cosine 30 degrees, cosine 60 degrees. Let's see which one of those is our easier value. Let's start with a 1/2. So let's start with sine of 30 degrees. Sine of 30 degrees is 1/2. Sine is opposite over hypotenuse. So sine of 30 degrees is 1/2. I know that that is a true statement, that no matter the size of my triangle, the sine of a 30-degree angle is going to be equal to 1/2. And in this case, the sine of this 30-degree angle is y over 9. That's going to be equal to y over 9. So I have a proportion that I can solve. And my only unknown is y. 1 times 9 is 9. That's going to be equal to 2y. So y is 9/2. So that's one unknown I figured out. Y is 9/2. Alright, so let's do, if sine of 30 degrees is 1/2, then I know that cosine of 30 degrees is square root 3 over 2. If I need to go look that up, I can look it up on my unit circle, or I can look it up here on this chart that I just filled in, my unit circle. 30-degree angle, cosine and sine. Sine and cosine for 30 degrees. So I know this is a true statement. Cosine is adjacent over hypotenuse. So my adjacent side here is x, and my hypotenuse is, my adjacent side is x, my hypotenuse is 9. Sorry, I got distracted. So I have another proportion that I can solve. 9 times square root 3 is equal to 2 times x. So x is 9 square roots of 3 over 2. Nine square root 3 over 2. So we need to do w and z. To do w and z, I'm going to need to switch to this other triangle. I can work with this 30-degree angle. I can work with this 60-degree angle. I'm going to have to use a found value here, right? Because I'm I don't have any given values for this triangle. So opposite over hypotenuse is going to be cosine or sine of 60 degrees. Sine of 60 degrees is opposite over hypotenuse. Sine of 60 degrees is square root 3 over 2. Same thing as cosine 30, sine of 60. And for this 60 degree angle, opposite over hypotenuse is going to be 9/2 over W. So I've got square root 3, this proportion I'm solving, square root 3W equals 2 times 9/2 is just 9. When I divide both sides by that square root 3, 9 over square root 3, I'm going to have to rationalize that. 9 square root 3 over 3 simplifies to 3 square roots of 3 for my value for W. 3 square root 3. And now I've got to figure out Z. So to figure out Z, I'm going to do cosine of 60 degrees. So cosine of 60 degrees, sine of 60 was square root 3 over 2, cosine of 60 is 1/2. Cosine is adjacent over hypotenuse, and I need to solve that proportion. 3 square root 3 equals 2 times Z. So Z is 3 square roots of 3 divided by 2. And I have solved all the missing values, the missing side lengths for those triangles. Alright, I have a second example on here. We are not going to work through it. I am, however, going to give you the answers so that you can work through it on your own and you can come back to make sure that you got it correct. T is 10 square roots of 6. What else have we got? R is 15 square roots of 2. P is 15. And Q comes out to be 5 square roots of 6. So those are the values that you should come out with on that triangle. I encourage you to go back and review what we did up here and then work through this one to make sure that you can find those 4 missing side lengths.